Okay, so in section 3.3, we looked at using properties of logarithms to help us rewrite logarithmic expressions. And now we are going to use those properties to help us with solving exponential and logarithmic equations. So let me get a color to start. So first, we want to try and use the one-to-one properties when possible to solve simple exponential and logarithmic equations. And basically what the one-to-one properties say is if you have b to the x power equal to b to the y power, that means that the exponents must be equal to each other. X must equal to y. Or same thought process, if we have the log base b of x equal to the log base b, so same bases there, of y, it means that those arguments x and y must also be equal to each other. So whenever possible, you want to try and use one-to-one property. We're going to be using these inverse properties. These are just properties we talked about in section 3.2 for logarithms. Okay, so let's look at solving these simple exponential equations, and we want to try and use one-to-one property. So like this first equation, 3 to the x equals to 81. Let's see if we can rewrite 81 as 3 raised to a power. And we can. So we can rewrite 81 as 3 to the 4th power, which means by the one-to-one property, x must be equal to 4. Sorry, I didn't leave very much room here. Okay, looking at the next equation, is it possible to rewrite 125 as 5 raised to a power? Yes, it is, right? So 5 to the 7 minus x power equals to 5 cubed. So that means that 7 minus x is equal to 3 by the one-to-one property. So then solving for x, we get that x is equal to 4 again. Okay. And then for 1/2 raised to the 4y power equal to 16, can we rewrite 16 as 1/2 raised to a power? Yes, we can. So 1/2, oops, not 1/4, 1/2 raised to the -4th power. Okay, so then we would have, by the one-to-one property, 4y equals to -4, or y equals to the -1. Okay, so when possible, we like to use one-to-one property. Okay, it's efficient, quick, clean. Okay, whenever possible. But we can't always use one-to-one property. So like 5y squared equals to 27. We cannot rewrite 27 as 5 raised to some integer power. Or 5 raised to some rational power. So we have options here. So the first way that you can think about this is to rewrite in the equivalent logarithmic form. Okay, so that would be the log base 5 of 27 is equal to y squared. And then finish solving for y. Y is equal to plus or minus the square root of the log base 5 of 27. Okay, these are the exact values of y. Okay, so those are your exact values for the solution. I'm going to, on your test, ask you for the exact values and then also the decimal approximations. So then, to get the decimal approximations, let's go ahead and type in the square root of log base 5 of 27. So we end up with y is approximately plus or minus 1.43 1. Okay, so that would be the decimal approximation. Decimal approximation. Okay, now the other approach here, where you'll get the exact same answer, but it's just a kind of different thought process, is to think about taking the log base 5 of each side of this equation. I'm going over here. So log base 5 of 5 to the y squared equals to the log base 5 of 27. Properties of logarithms, the left-hand side will become y squared equals to the log base 5 of 27, and you can see that we're back where we were over here when we just thought about rewriting in the logarithmic form. The third approach you could use, and I don't care as long as it's accurate, would to just be to take the log. You can actually take the log base anything of each side of the equation. But if you took, let's just say the log base 10 of each side, okay, then you could plug the left side, okay, and then divide by log of 5 on each side. Okay, notice right here, by change of base formula, this is equal to the log base 5 of 27. So then when we finish solving, we get y equals to plus or minus the square root of log of 27 over the log of 5, and you'll end up with the same decimal approximation. I do not care which method you use. It just needs to be correct. Okay, so I'm going to stick with, and I think it's the most efficient, to think about rewriting, when possible, in the equivalent logarithmic form. So for this next equation, we're trying to solve for x, so log base 4 of 71 is equal to 3x plus 2, right? 4 to that power equals to 71. Okay, so log base 4 of 71 is just a number. So we need to finish isolating x. We can subtract by 2 and divide by 3. This is our exact solution. This is the exact value. So I need to see that. Now, if you used one that, like if you took the log of each side of the equation, your exact value might look slightly different than mine. That's fine. Okay, so then x, once you pop that into your calculator, so math, log base 4 of 71 minus 2. So you're going to be able to use your calculator on this test. It's going to be very important that you are showing all of your work to receive full credit. Okay, 1.018 is the decimal approximation for x. Okay. For the next equation, I would first divide by 4 before we even think about taking the log of each side of the equation or rewriting in logarithmic form. So divide by 4 on each side, so we'll get e to the x squared is equal to 16. So its equivalent logarithmic form would be ln, right, log base e of 16 equals to x squared. So x equals plus or minus the square root of ln of 16. Okay, so those are exact values for the solution. Running out of room, so come up here. So x equals approximately plus or minus. I'll type that into the calculator. 1.665. Okay, so here you also, in this step, you could have thought about taking the natural log of each side of the equation and then plug to get the x squared. Pull down, or actually that's a property, huh? Because the bases would have matched, that would have, the left-hand side would have just been equal to x squared. Okay. Next, switch colors. All right, so rewriting in logarithmic form. So the log base 10, I don't need to write the 10, of 7 equals to 2x minus 3. Get x by itself by adding 3 and dividing by 2. Okay, and then log 7 plus 3 divided by 2. I get 1.923. Okay, so notice that this exponential equation looks sort of kind of like a quadratic, kind of sort of. So you have two options. You can either try and factor this with guess and check. Okay. Not always possible. So I suggest the method that I'm about to show you just because it kind of leads to skills for next year. But also then if you need to apply quadratic formula, it's a little bit easier. So why don't we let u, we're going to do u substitution. So let's let u equal e to the x. So we can rewrite the equation replacing all the e to the x's with u. So we'll have u squared minus 4u plus 3 equals to 0. I believe that factors. So u minus 3 and u minus 1. So we get u equals to 3 or u equals to 1, but we're not solving for u. So we need to replace the u's with e to the x again. Okay. The equation on the right we can solve by inspection, right? X has to be equal to 0. And on the left side, if we either think about taking the natural log of each side of the equation or rewriting in logarithmic form, it would be x equals to ln of 3. Okay, so x is approximately 1.099. We have two solutions. So we've been solving exponential equations so far, simple ones and then not so simple ones. So now we're going to look at logarithmic equations. Now the thing about logarithmic equations is you need to always check for extraneous solutions. And the reason is exponential equations, exponential functions have domains of all real numbers, right? The exponents can be any real number and you will still have a real number output. Logarithmic functions, not the same thing, right? You can only evaluate logarithms for values strictly greater than 0. So you could determine the domain of this equation or determine what the domain restrictions are, or you could just remember to check for extraneous solutions. So that's what my suggestion is going to be. So let's first go ahead and use product rule to rewrite this as a single, the right hand side as a single logarithm. So we'll have the ln of x plus 8 equals ln of x times x plus 3. Where now, because we have ln on each side of the equation, so log base e on each side, we can, by the one-to-one property, say, well, x plus 8 has to be equal to x squared plus 3x. right? The arguments have to be equal to each other by the one-to-one property. And now we just have a quadratic equation. Is that factorable? X plus 4x minus 2. So x equals to -4 or x equals to 2. But check for extraneous solutions by either writing it out or thinking about plugging your solutions into the original equation. Now, -4 is actually going to be an extraneous solution because if you plug -4 in here or here, you'll be taking the natural log of a negative number, which is not possible. So this is, -4 is an extraneous solution. However, x equals to 2 works. Okay. So what sticks out to me here, oh, this is just 1. So this is the log base 2 of 4x minus 1 equals to 2. Add 1 to each side of the equation. And now let's rewrite this in exponential form. So 2 cubed equals to 4x. So 8 equals to 4x, or x is equal to 2. Check for extraneous solutions. If we substitute 2 in for x there, that works. Log base 2 of 8 is just 3, and then so 3 minus 1 is 2. That works. 2 is the solution. Okay, so this, it's already given to you. This logarithmic equation will have no solution, but let's see what happens to get us there. So let's rewrite this in its exponential form. So e to the 7th power is equal to 3 minus x squared, right? E to the 7th power equals 3 minus x squared. Okay, so then that'll be e to the 7th minus 3 equals negative x squared. Divide by -1 on each side. Okay. And then if we try taking the square root of each side. Now here's the thing. Negative e to the 7th power is going to be a pretty small number. And then plus 3, I'm thinking this is going to be a negative number. So remember, when we take the square root of a negative number, we get an imaginary number. So I'm thinking that there's actually, know that. I would get a domain error if I pop this into my calculator. So because this is negative, okay, we're going to have no real solution here. We only care about the real solutions. No real solutions. All right, so we looked at solving word problems like this using our calculator already, but now let's look at how we can solve using algebra. So you saved $1,000 from a summer job and put it in a CD earning 5% compounding continuously. So that means that we're using PERT, the PERT formula. Okay. So P is the initial amount, the principal. So we want to know how many years it will take for your money to double. Okay, so if the initial amount is 1,000, the rate is 5%, so 0.05. We're solving for t, and we want to know how long it'll take for it to double. Well, 1,000 times 2 would be 2,000. We can divide by 1,000 on each side, though, to make this simpler. Okay. And then you can think about taking the natural log of each side of the equation, or just rewriting in its equivalent logarithmic form, which would be ln of 2 is equal to 0.05t. Dividing by 0.05 on each side of the equation, you'll get ln of 2 over 0.05. So that's the exact value of t. So if we pop that in the calculator, we get t is approximately 13.863 years. And it's just to round to the nearest year. So it will take approximately 14 years for your money to double. This is the one you could have also, in your calculator, typed in y sub 1 equals to 2, y sub 2 equals to e to the 0.05t, and then found the point of intersection. You would have gotten the same thing.